Have you ever noticed how shadows follow you everywhere? They stretch long in the morning, disappear at noon and grow again as evening approaches. We live surrounded by these dark companions, yet most of us never pause to consider what they truly are. Every single day, shadows shape our world in ways we rarely acknowledge. The cool relief you feel when stepping under a tree on a hot summer day comes from entering its shadow. The dramatic silhouettes we see at sunset exist because light cannot reach certain areas. Even the simple act of reading this involves shadows. The dark letters on your screen are essentially tiny shadows formed by blocked light. But here lies something curious about human nature. We take shadows for granted precisely because they seem so ordinary. We assume we understand them completely. After all, what could be simpler than darkness where light should be? This assumption, however, leads us to overlook a fascinating question that challenges our basic understanding of the physical world. Shadows feel real to us. They have boundaries we can see, shapes we can recognize, and effects we can measure. When you place your hand between a lamp and a wall, you create something that seems to have presence and form. So here is the question that will guide our exploration. Could something as seemingly empty as a shadow actually have weight? Consider this carefully. We know that many things in our universe have mass. The air you breathe, the chair you sit on, even the light streaming through your window carries energy. But what about the absence of light? What about the darkness itself? This question might sound absurd at first. How could nothing weigh something? Yet the more we examine shadows, the more intriguing this possibility becomes. After all, if shadows can block heat, create cooling effects and influence the growth of plants, might they possess other properties we have not yet discovered? The search for an answer to this question will take us on a journey through some of the most fundamental concepts in physics. We will explore the nature of light itself, examine the relationship between energy and mass, and even venture into the strange world of quantum mechanics, where our everyday intuitions often fail us. What makes this investigation particularly compelling is that it forces us to question our most basic assumptions about reality. We think we know what shadows are, but do we really? We assume that absence means nothing, but what if the absence of something as powerful as light creates effects we have not yet learned to measure? The answer to whether shadows have mass will surprise you, but the journey to that answer will reveal something even more remarkable. How much we can learn about the universe by asking questions that seem impossibly simple. Throughout human history, the greatest scientific discoveries have often emerged from examining the things we thought we already understood. Newton wondered why apples fall down rather than up. Einstein questioned what would happen if you could ride alongside a beam of light. Today, we are asking whether the absence of light might have measurable weight. This question connects to fundamental principles that govern everything from the smallest particles to the largest structures in the universe. The answer will not only satisfy our curiosity about shadows, but will also illuminate the profound relationship between light, energy, and matter itself. Before we can determine whether shadows have mass, we must first understand what shadows actually are. This understanding will reveal that shadows are far more interesting than most people realize, and their true nature holds the key to answering our central question. The story of shadows begins with light, and the story of light begins with some of the most beautiful and surprising discoveries in all of science. Understanding shadows requires us to examine the fundamental process that creates them. This process involves light, objects, and the spaces between them in ways that reveal surprising complexity beneath what appears simple. When light travels from any source and encounters an obstacle in its path, that obstacle prevents the light from continuing in its original direction. The region behind the obstacle where light cannot reach becomes what we call a shadow. This basic mechanism operates whether the light source is the sun, a candle, or the screen you're viewing right now. The critical insight here is that shadows are not things that exist independently. They are regions defined entirely by the absence of light. A shadow has no substance of its own. It possesses no material properties. It is simply a description of where light is not present. This absence, however, creates observable effects in the physical world. The temperature difference between sunlit areas and shadowed areas demonstrates that the presence or absence of light produces measurable consequences. Plants grow differently in shadows compared to direct sunlight, proving that this absence influences biological processes. These effects occur not because shadows themselves act upon the world, but because the energy that light would have provided is missing. Light travels in perfectly straight lines through empty space and continues in straight lines through transparent materials unless something deflects or absorbs it. This fundamental property of light determines the precise shape and position of every shadow. The sharp edges of shadows cast by small, distant light sources occur because light cannot bend around corners under normal circumstances. When you observe how shadows change throughout the day, you are witnessing the geometric relationship between light source, object, and surface. As the sun moves across the sky, the angle at which light strikes objects changes, causing shadows to shift in both direction and length. This movement demonstrates that shadows are purely geometric phenomena determined by the straight line propagation of light. The size and clarity of shadows depend entirely on the characteristics of the light source creating them. A small, bright light source produces sharp shadows with clearly defined edges. A large, diffuse light source creates softer shadows with gradual transitions from light to dark. Multiple light sources produce multiple overlapping shadows, each following the same geometric principles. These observations lead us to an important conclusion about the nature of shadows. Since shadows are simply regions where light is absent, they cannot possess any properties that require physical substance. They cannot have temperature, density, or electrical charge because they are not made of anything. They are locations defined by what is missing rather than what is present. However, this absence of light has consequences that extend beyond simple darkness. Light carries energy, and this energy affects everything it encounters. When light strikes a surface, it can heat that surface, cause chemical reactions, or even exert physical pressure. The absence of this energy in shadowed regions means that different physical processes occur there compared to illuminated areas. Light exhibits properties that challenge our everyday understanding of what constitutes matter and energy. Photons, the fundamental particles of light, have no mass when at rest, yet they carry momentum and energy. They travel at the fastest possible speed in the universe and can transfer their energy to other objects when they interact with matter. This dual nature of light, as both wave and particle, becomes relevant to our investigation of shadows because it determines exactly what is absent in a shadowed region. When we ask whether shadows have mass, we are really asking whether the absence of these massless but energetic particles creates any measurable physical effect equivalent to mass. The energy carried by light can be substantial. Solar panels convert this energy into electricity. Solar sails use the momentum of photons to propel spacecraft. The heat you feel from sunlight on your skin results from light energy being absorbed and converted to thermal energy. All of these effects demonstrate that while light has no rest mass, it definitely carries energy and momentum. In shadowed regions, this energy and momentum are absent. The question becomes whether this absence creates any physical effect that could be interpreted as negative mass, or whether shadows remain truly neutral with respect to all physical properties, including mass. The formation of shadows reveals fundamental principles about how light behaves in our universe. Light travels at constant speed in straight lines, carries energy and momentum despite having no rest mass, and creates measurable effects wherever it goes. Shadows mark the boundaries of light's influence, creating regions where these effects do not occur. This understanding prepares us to examine more deeply what light actually is, and how its unique properties might relate to our central question about the mass of shadows. Light represents one of the most fundamental forces in our universe, yet its true nature challenges our everyday understanding of matter and energy. To determine whether shadows possess mass, we must first comprehend what light actually is and how it interacts with the physical world. Light consists of particles called photons. These particles possess extraordinary properties that distinguish them from all other forms of matter. Photons have no rest mass, meaning they weigh nothing when stationary. However, photons never remain stationary. They travel at approximately 300,000 kilometers per second, the fastest speed possible in our universe. Despite having no rest mass, photons carry both energy and momentum. This combination creates a fundamental paradox that helps explain many phenomena in physics. When photons strike an object, they can transfer their momentum to that object, causing it to move. This transfer of momentum occurs even though the photons themselves have no mass in the traditional sense. The energy carried by photons varies depending on their frequency or color. Blue light carries more energy per photon than red light. Ultraviolet light carries even more energy, which explains why it can cause sunburn and other chemical reactions. This energy content determines how strongly light can affect the materials it encounters. When photons interact with matter, they can produce measurable physical effects. Solar panels convert photon energy into electrical current. The warmth you feel from sunlight results from photons transferring their energy to your skin. Even the fading of colors in fabrics exposed to sunlight occurs because photons carry enough energy to break chemical bonds in dye molecules. One of the most striking demonstrations of light's physical power involves radiation pressure. Although individual photons exert tiny forces, large numbers of photons can create measurable pressure on objects. Scientists have proposed using this radiation pressure to propel spacecraft through space using solar sails. These sails would capture the momentum from photons emitted by the sun, gradually accelerating the spacecraft without requiring fuel. Laboratory experiments confirm that light exerts pressure on objects. Devices called radiometers demonstrate this effect visibly. These instruments contain lightweight vanes that rotate when exposed to light, driven by the momentum transfer from photons. The rotation occurs because photons striking the vanes transfer their momentum, creating a force that causes movement. The electromagnetic spectrum extends far beyond visible light, encompassing radio waves, microwaves, infrared radiation, ultraviolet light, X-rays and gamma rays. All of these forms of electromagnetic radiation consist of photons differing only in their energy content and frequency. This entire spectrum behaves according to the same physical principles, carrying energy and momentum despite having no rest mass. Infrared radiation, which we perceive as heat, demonstrates how electromagnetic energy affects matter at the molecular level. When infrared photons strike molecules, they cause those molecules to vibrate more rapidly, increasing the temperature of the material. This process explains how the sun heats the Earth and how heat lamps warm objects without direct contact. The dual nature of light as both wave and particle creates complex interactions with matter. When light behaves as a wave, it can interfere with itself, creating patterns of bright and dark regions. When light behaves as a particle, individual photons can be detected and counted. This duality affects how light creates shadows and determines what properties those shadows might possess. Understanding photon behavior becomes crucial when considering shadows because shadows represent regions where photons are absent. If photons carry energy and momentum, then shadowed regions lack this energy and momentum. The question becomes whether this absence creates any physical effect that could be measured as negative mass, or whether shadows remain completely neutral. The speed of light provides another important consideration. Because photons travel at the maximum possible speed in the universe, they cannot be slowed down or stored in the conventional sense. Light either exists at full speed or does not exist at all. This property means that shadows form and disappear instantaneously as objects move to block or allow light passage. Temperature measurements reveal one of the most obvious effects of light's energy. Surfaces exposed to direct sunlight become warmer than surfaces in shadow. This temperature difference occurs because photons transfer their energy to illuminated surfaces, while shadowed surfaces receive no such energy input. The magnitude of this temperature difference depends on the intensity of the light and the properties of the surface material. These temperature effects extend beyond simple heating. Many chemical reactions proceed at different rates depending on temperature, meaning that shadowed and illuminated regions can experience different chemical processes. Biological systems also respond differently to temperature variations, affecting growth rates and metabolic processes in shadowed versus illuminated areas. The physical effects of light extend to the atomic level. Photons can excite electrons in atoms, causing them to jump to higher energy levels. When these electrons return to lower energy levels, they emit new photons. This process underlies fluorescence, phosphorescence, and many other optical phenomena. Shadows represent regions where these atomic-level interactions cannot occur due to the absence of photons. Light's ability to carry information also distinguishes it from other forms of energy. The patterns of light and shadow that reach our eyes allow us to perceive shapes, colors, and movements in our environment. This information-carrying capacity of light enables all forms of optical communication and imaging technology. Having established that light carries energy and momentum, despite having no rest mass, we can now examine how these properties relate to the fundamental relationship between energy and mass in our universe. The relationship between mass and energy represents one of the most profound discoveries in the history of science. This relationship, expressed through Einstein's famous equation E = mc², fundamentally changes how we understand the physical world and provides the key to answering whether shadows possess mass. Einstein's equation reveals that mass and energy are not separate properties, but rather different manifestations of the same underlying reality. The equation states that energy equals mass multiplied by the speed of light squared. This mathematical relationship means that any system containing energy will have an effective mass, and conversely, any mass can be converted into energy under the right conditions. The implications of this mass-energy equivalence extend far beyond theoretical physics. Nuclear reactions in power plants and the sun demonstrate mass converting to energy on a massive scale. When atomic nuclei combine or split, small amounts of mass disappear and reappear as tremendous amounts of energy. The sun generates its energy by converting approximately 4 million tons of mass into pure energy every second through nuclear fusion reactions. This relationship between mass and energy applies to all forms of energy, including the energy carried by light. Although individual photons have no rest mass, the energy they carry contributes to the total mass of any system that contains them. This contribution creates measurable effects under certain conditions. Consider a perfectly sealed container that traps light inside, preventing any photons from escaping. The energy of these trapped photons increases the total mass of the container system. If you could measure the mass of this container before and after filling it with light, you would find that the light-filled container has slightly more mass than the empty container. The difference equals the energy of the trapped light divided by the speed of light squared. This effect, while real, remains extremely small under normal circumstances. Light carries relatively little energy compared to the mass of typical containers, making the mass increase nearly impossible to detect with ordinary measuring instruments. However, the principle applies universally. Any system containing electromagnetic energy will have a correspondingly increased mass. The mass-energy relationship also works in reverse. When energy leaves a system, the system's mass decreases accordingly. This principle applies to all forms of energy transfer, whether through radiation, conduction, or any other mechanism. The mass changes remain tiny in everyday situations, but become significant in high-energy processes involving nuclear reactions or particle physics. Understanding this relationship helps clarify what happens in regions where light is present versus regions where light is absent. Areas receiving light experience a continuous input of energy in the form of photons. This energy contributes to the total mass energy content of the system, albeit in extremely small amounts. Shadowed areas receive no such energy input, and therefore lack this contribution to their mass energy content. The question of whether shadows have mass thus becomes a question of whether the absence of light's energy contribution creates a measurable effect. Since shadows are simply regions where light is not present, they cannot possess negative mass. The absence of energy does not create negative energy, just as the absence of mass does not create negative mass. However, the mass-energy relationship suggests that systems in shadow may have slightly less mass energy content than identical systems in light, purely because they lack the energy contribution from photons. This difference would be extraordinarily small and practically unmeasurable under normal conditions, but it represents a real physical effect predicted by Einstein's equation. The practical implications of mass-energy equivalence extend to many technologies we use daily. Medical imaging devices that use radioactive tracers rely on mass-energy conversion to generate detectable radiation. Solar panels convert photon energy into electrical energy, demonstrating the relationship between electromagnetic energy and other forms of energy. Even the GPS satellites orbiting Earth must account for mass-energy effects to maintain accurate positioning data. In the context of shadows, the mass-energy relationship reveals that while shadows themselves cannot have mass, the absence of light in shadowed regions means those regions lack the tiny mass-energy contribution that photons would provide. This absence does not create negative mass, but rather represents a neutral state where no additional mass energy exists beyond that of the matter already present. The relationship between mass and energy also explains why massless particles like photons can carry momentum and exert forces on other objects. The momentum of a photon equals its energy divided by the speed of light. This momentum allows photons to transfer force to objects they strike, even though the photons themselves have no rest mass. When photons are absent in shadowed regions, this momentum transfer cannot occur. Einstein's equation furthermore predicts that any object emitting or absorbing light will experience corresponding changes in mass. A hot object radiating infrared light gradually loses mass as it cools, while an object absorbing light gains mass. These changes remain imperceptibly small in everyday situations, but become measurable in precision experiments involving high-energy processes. The universal nature of mass-energy equivalence means that it applies to all phenomena involving energy transfer, including the formation and movement of shadows. When an object blocks light to create a shadow, it absorbs or reflects the photons that would otherwise continue traveling. This interaction involves energy transfer and therefore minute mass changes, though these changes occur in the light-blocking object rather than in the shadow itself. This understanding of mass-energy relationships provides the foundation for examining whether shadows can be measured or detected through their effects on mass. The principles established by Einstein's equation will guide our investigation into whether the absence of light creates any measurable physical consequences that could be interpreted as mass-related phenomena. The fundamental question of whether shadows possess measurable mass requires us to examine what happens when we attempt to detect mass differences between illuminated and shadowed regions. This investigation reveals the distinction between theoretical possibilities and practical measurements in physics. Classical physics provides a clear answer regarding shadow mass. According to traditional mechanical principles, shadows cannot possess mass because they consist of empty space where light is absent. Mass requires matter, and shadows contain no additional matter beyond what already exists in the space they occupy. A shadow represents a geometric region defined by the absence of photons, not the presence of any material substance. Direct measurement attempts confirm this classical understanding. When identical objects are placed on precision scales, one in direct light and another in shadow, the scales register identical masses within the limits of measurement accuracy. The gravitational force acting on each object remains the same regardless of illumination conditions, indicating that shadows add no measurable mass to the systems they encompass. However, the absence of light does create subtle physical effects that merit careful examination. Shadowed regions experience different environmental conditions compared to illuminated areas, and these differences can influence measurement precision in ways that might initially appear related to mass changes. Temperature represents the most obvious difference between illuminated and shadowed regions. Objects in direct sunlight absorb photon energy and warm up, while objects in shadow remain cooler due to the absence of this energy input. This temperature difference affects the density of air surrounding the objects, which can influence precision measurements through buoyancy effects. When air warms up, it expands and becomes less dense. Cooler air in shadowed regions remains denser than warmer air in illuminated regions. This density difference creates slight variations in the buoyant force that air exerts on objects placed in these regions. Precision scales can detect these buoyancy changes, but they result from air density variations rather than mass changes in the objects themselves. Atmospheric pressure also varies slightly between illuminated and shadowed regions due to temperature-driven air movement. Warmed air rises while cooler air sinks, creating minor pressure differentials. These pressure changes can affect sensitive measuring instruments, particularly those that rely on air pressure for calibration or operation. Radiation pressure provides another subtle effect that differs between illuminated and shadowed regions. Photons striking objects exert tiny forces through momentum transfer. Objects in direct light experience continuous photon bombardment, while objects in shadow experience no such radiation pressure. The magnitude of this effect remains extremely small under normal conditions but becomes measurable with sufficiently sensitive equipment. The cumulative effect of radiation pressure from sunlight amounts to approximately 9 micronewtons per square meter of surface area. This force is millions of times smaller than the weight of typical objects, making it undetectable by ordinary scales. However, this pressure difference between illuminated and shadowed regions does represent a real physical phenomenon that could theoretically influence precision measurements. Scientific instruments designed to measure mass differences between illuminated and shadowed regions must therefore account for multiple environmental factors that can mask or mimic the effects they seek to detect. Temperature control, air pressure stabilization, and electromagnetic shielding become necessary to isolate any genuine mass-related phenomena from these secondary effects. Controlled laboratory experiments have been conducted to search for mass differences attributable to shadows themselves rather than environmental factors. These experiments typically involve placing identical objects in carefully controlled illuminated and shadowed environments while monitoring for mass changes using the most sensitive available instrumentation. Results from these controlled experiments consistently show no detectable mass difference attributable to shadows themselves. Any observed variations in measurements can be accounted for by environmental factors such as temperature changes, air density variations, or electromagnetic interference. The shadows themselves contribute no measurable mass to the experimental systems. The limits of measurement precision play a crucial role in interpreting these experimental results. Current technology can detect mass changes on the order of micrograms under ideal conditions. However, the theoretical mass effect of light's energy contribution, based on Einstein's mass-energy equivalence, would be many orders of magnitude smaller than this detection threshold for typical laboratory conditions. Even if shadows did affect mass through the absence of light's energy contribution, this effect would be approximately 10 to the negative 15th grams for ordinary lighting conditions. This magnitude falls far below the sensitivity limits of any currently available measuring equipment, making direct detection impossible with existing technology. The practical implications of these measurement limitations suggest that while shadows may theoretically lack the infinitesimal mass-energy contribution of photons, this absence cannot be detected through direct weighing methods. The effect, if it exists, remains too small to measure against the background of environmental influences and instrument limitations. These measurement challenges highlight an important principle in experimental physics: the distinction between theoretical predictions and observable phenomena. While mass-energy equivalence predicts that the absence of light should correspond to the absence of light's energy contribution to mass, this prediction cannot be verified through direct measurement under normal circumstances. The investigation of shadow mass through direct measurement thus reveals more about the limits of experimental precision than about the fundamental nature of shadows themselves. These limits point towards the need for alternative approaches to understanding whether shadows possess any measurable physical properties related to mass. The quantum realm operates according to principles that fundamentally differ from our everyday experience of the physical world. At the smallest scales of matter and energy, particles exhibit behaviors that challenge our conventional understanding of presence and absence. Examining shadows through this quantum perspective reveals new complexities in the question of whether they possess mass. Quantum mechanics describes particles as existing in states of probability rather than definite locations or properties. Electrons, photons, and other fundamental particles do not follow the predictable paths we observe in larger objects. Instead, they exist as wave-like probability distributions that describe where they might be found when measured. This wave-particle duality applies to all matter and energy in the universe, though its effects become negligible for objects larger than atoms. The quantum nature of light becomes particularly relevant to understanding shadows. Photons, the particles that compose light, exhibit quantum properties that differ significantly from classical particles. When photons encounter obstacles or pass through narrow openings, they create interference patterns that demonstrate their wave-like characteristics. These patterns include regions of enhanced brightness and regions of darkness that extend beyond simple geometric shadows. The famous double-slit experiment illustrates how quantum effects create shadow-like phenomena that cannot be explained through classical physics. When individual photons pass through two closely spaced openings, they interfere with themselves to create alternating bright and dark bands on a detection screen. The dark bands represent regions where photons have zero probability of arrival, creating quantum shadows that exist due to wave interference rather than simple geometric blocking. These quantum interference effects occur even when photons pass through the apparatus one at a time, indicating that each individual photon somehow interacts with both openings simultaneously. The resulting pattern of bright and dark regions emerges from the wave-like nature of photons rather than from any classical shadow-casting mechanism. This phenomenon demonstrates that quantum mechanics can create regions of darkness through fundamentally different processes than geometric shadow formation. Quantum field theory introduces another layer of complexity to our understanding of empty space and shadows. According to this theory, what we perceive as empty space actually contains fluctuating quantum fields that constantly create and destroy virtual particle pairs. These virtual particles exist for extremely brief periods before annihilating each other, but their presence means that truly empty space does not exist at the quantum level. Virtual particles appear and disappear throughout all regions of space, including areas we would classically consider to be shadows. The energy associated with these quantum fluctuations contributes to the total energy content of space itself. However, this contribution remains the same whether a region is illuminated or shadowed, since virtual particle creation depends on quantum field properties rather than the presence or absence of real photons. The quantum vacuum state represents the lowest possible energy condition for any region of space, but this state still contains energy due to quantum fluctuations. This vacuum energy exists equally in illuminated regions and shadows, providing no net contribution to mass differences between these areas. The quantum nature of empty space, therefore, does not create measurable mass effects specific to shadows. Quantum mechanics also affects how we understand the interaction between light and matter at the atomic level. When photons strike atoms, they can cause electrons to jump between energy levels through processes called absorption and emission. These quantum transitions occur in discrete steps rather than continuously, and they determine how materials interact with light of different frequencies. In shadowed regions where photons are absent, these quantum transitions cannot occur through photon absorption. However, atoms in shadows still undergo spontaneous emission processes where excited electrons return to lower energy states while emitting photons. These emission processes occur according to quantum mechanical probabilities and continue regardless of external illumination conditions. The uncertainty principle, another fundamental aspect of quantum mechanics, places limits on how precisely we can simultaneously measure certain properties of particles. This principle affects our ability to determine exact photon positions and energies, introducing inherent uncertainties into any measurements of light-related phenomena, including shadow properties. Quantum entanglement represents one of the most peculiar aspects of quantum mechanics, allowing particles to maintain instantaneous correlations regardless of the distance separating them. While entanglement effects do not directly influence shadow formation or mass properties, they demonstrate how quantum mechanics permits phenomena that have no classical analogues. These non-classical effects remind us that quantum systems can exhibit properties that exceed our everyday intuitions about physical reality. The application of quantum mechanics to the question of shadow mass reveals that quantum effects do not create measurable mass in shadows. While quantum fluctuations ensure that no region of space is truly empty, these fluctuations exist equally in illuminated and shadowed areas. The quantum properties of light create interference patterns and probability distributions that can produce regions of darkness. But these quantum shadows do not possess mass any more than classical geometric shadows. Quantum field theory does predict that the energy of quantum fluctuations contributes to the curvature of space-time through gravitational effects. But this contribution remains constant across all regions of space regardless of classical illumination conditions. The quantum vacuum, therefore, provides no mechanism by which shadows could acquire mass or gravitational influence distinct from their surroundings. The exploration of quantum effects in relation to shadows ultimately reinforces the conclusion that shadows lack mass while revealing the rich complexity of physical phenomena at microscopic scales. Quantum mechanics expands our understanding of how light and matter interact, but it does not alter the fundamental conclusion that regions of absent light cannot possess mass properties. This quantum perspective prepares us to synthesize our findings and reach a definitive answer to the question of whether shadows have mass, incorporating insights from classical physics, relativity, and quantum mechanics into a comprehensive understanding of these ubiquitous phenomena. Our comprehensive investigation across classical physics, relativity theory, and quantum mechanics leads to a definitive conclusion regarding the fundamental question of whether shadows possess mass. The evidence from multiple scientific perspectives converges on a clear answer that resolves this inquiry while illuminating broader principles about the nature of physical reality. Shadows possess no mass whatsoever. This conclusion emerges directly from the fundamental definition of what shadows represent in physical terms. Shadows are regions where light is absent due to geometric obstruction by opaque objects. They constitute areas of space that lack photons but contain no additional matter or energy beyond what already exists in those locations. Since mass requires the presence of matter or energy, and shadows represent the absence of both photons and any substitute material, they cannot possess mass under any circumstances. The absence of light in shadowed regions does create measurable physical effects, but these effects do not translate into mass properties. Temperature differences between illuminated and shadowed areas result from the presence or absence of photon energy input. These temperature variations affect air density, atmospheric pressure, and thermal radiation patterns in ways that can influence sensitive measurements. However, these effects stem from environmental changes rather than from any intrinsic mass properties of the shadows themselves. Einstein's mass-energy equivalence principle confirms that while the energy carried by photons contributes infinitesimally to the mass of systems containing light, the absence of this energy in shadows does not create negative mass. The relationship between mass and energy operates in one direction only. Energy contributes to effective mass, but the absence of energy simply results in the absence of that contribution rather than producing negative mass effects. Radiation pressure represents another measurable consequence of light's presence that disappears in shadowed regions. Photons transfer momentum to objects they strike, creating forces that can be detected with sufficiently sensitive instruments. Objects in shadows experience no radiation pressure because no photons arrive to transfer momentum. This absence of force does not constitute negative mass, but rather represents a neutral condition where no additional forces operate beyond those already present. The quantum mechanical examination of shadows reveals that even at the smallest scales, where virtual particles constantly appear and disappear in empty space, shadows do not acquire mass properties. Quantum fluctuations occur equally in illuminated and shadowed regions, providing no net mass difference between these areas. The wave-like nature of photons can create interference patterns that produce regions of darkness through quantum effects. But these quantum shadows lack mass, just as classical geometric shadows do. Scientific measurements using the most sensitive available instruments confirm the theoretical prediction that shadows possess no detectable mass. Controlled experiments that account for environmental variables such as temperature, air pressure, and electromagnetic interference consistently show no mass differences attributable to shadows themselves. The limits of current measurement precision exceed the theoretical magnitude of any mass effects that might result from the absence of light's minimal energy contribution. This definitive answer regarding shadow mass reveals important insights about the nature of absence in physics. The physical world operates according to principles where effects result from the presence of matter, energy and forces rather than from their absence. Absence can create observable consequences by removing sources of energy, momentum or other physical influences, but absence itself cannot generate new physical properties such as mass. The investigation of shadow mass demonstrates how seemingly simple questions can illuminate fundamental principles of physics. The absence of mass in shadows reflects the broader principle that physical properties require physical substances or energies to manifest. Empty space, whether in shadows or in the vacuum between stars, cannot possess properties that require material presence or energy density. Understanding that shadows lack mass also clarifies their role in various natural and technological processes. Shadows influence plant growth, animal behavior, and human comfort through their effects on temperature and light availability, rather than through any gravitational or mass-related mechanisms. Solar panels and other light-sensitive technologies respond to shadows through the absence of photon energy, rather than through any mass-related interactions. The temperature effects created by shadows extend beyond simple heating and cooling to influence chemical reaction rates, biological processes, and material properties. These effects occur because molecular and atomic processes depend on energy input from photons. In shadowed regions where this energy input is absent, different physical and chemical processes predominate. These changes result from energy availability rather than from any mass properties of the shadows themselves. Biological systems demonstrate particularly clear examples of how shadow effects operate through energy availability rather than mass interactions. Plants exhibit phototropism, growing toward light sources to maximize photon absorption for photosynthesis. This behavior responds to the presence or absence of light energy, rather than to any gravitational effects from shadows. Similarly, human circadian rhythms respond to light and shadow cycles through neurochemical pathways, triggered by photon detection, rather than through mass-sensitive mechanisms. The absence of mass in shadows has implications for how we understand the relationship between geometry and physics. Shadows represent purely geometric phenomena determined by the straight-line propagation of light and the positions of light sources and obstacles. This geometric nature explains why shadows can have sharp boundaries, definite shapes, and predictable movements without possessing any material properties themselves. Weather patterns and climate systems provide additional examples of how shadow effects operate through energy balance rather than mass interactions. Cloud shadows reduce solar heating of Earth's surface, affecting local temperature and wind patterns. These meteorological effects result from changes in energy input rather than from any gravitational influences of the shadows themselves. The conclusion that shadows possess no mass resolves our central question, while opening new avenues for understanding how absence influences physical systems. Shadows affect the world around them, not through their own properties, but through their role in determining where light energy is and is not available to drive physical, chemical, and biological processes. Our scientific journey through the fundamental properties of light, energy, mass, and quantum mechanics has provided a comprehensive answer to the question of whether shadows possess mass. The investigation has revealed far more than a simple yes or no response. illuminating the intricate relationships between light, matter, and the physical forces that govern our universe. The evidence from every branch of physics examined confirms that shadows possess no mass. Classical mechanics demonstrates that shadows represent geometric regions where light is absent rather than locations containing additional matter. Relativity theory shows that while light's energy contributes infinitesimally to system mass through mass-energy equivalence, the absence of light in shadows creates no corresponding negative mass. Quantum mechanics reveals that even at the smallest scales, where virtual particles fluctuate in empty space, shadows acquire no special mass properties that distinguish them from other regions of space. This conclusion carries profound implications for our understanding of how absence operates in the physical world. Shadows influence their surroundings not through possessing properties of their own, but through removing the effects that light would otherwise provide. Temperature differences, altered biological processes, and changed chemical reaction rates in shadowed regions all result from the absence of photon energy, rather than from any intrinsic properties of darkness itself. The investigation process has demonstrated how deceptively simple questions can lead to deep explorations of fundamental physics principles. What began as curiosity about shadow mass expanded into examinations of photon behavior, electromagnetic radiation, mass-energy relationships, quantum field theory, and the nature of empty space. Each area of investigation contributed essential insights while building toward the comprehensive understanding we have achieved. Scientific inquiry thrives on questions that challenge our assumptions about familiar phenomena. Shadows represent one of the most common experiences in daily life, yet few people consider their fundamental nature or question whether they might possess unexpected properties. The willingness to examine obvious things with scientific rigor often leads to discoveries that advance our knowledge of natural laws and physical principles. The techniques and principles employed in investigating shadow mass apply broadly to other scientific questions. The systematic examination of phenomena through multiple theoretical frameworks, the careful distinction between direct effects and environmental influences, and the recognition of measurement limitations all represent standard approaches in experimental physics. These methods enable scientists to distinguish between genuine physical effects and spurious correlations that might mislead casual observations. Modern physics continues to reveal counterintuitive properties of light that expand our understanding beyond classical expectations. Photons exhibit wave-particle duality, carry momentum despite having no rest mass, participate in quantum entanglement across vast distances, and contribute to the fabric of space-time through their energy content. These remarkable properties of light make the absence of light in shadows all the more significant by contrast. The relationship between light and shadow extends throughout the natural world in ways that demonstrate the fundamental importance of photon energy in driving physical and biological processes. Photosynthesis depends entirely on photon absorption to convert carbon dioxide and water into organic compounds. Solar heating drives weather patterns and ocean currents through differential energy input to illuminated and shadowed regions. Even human vision operates through detecting photons reflected from objects, with shadows providing contrast that enables shape and depth perception. Technological applications of light continue to expand as our understanding of photon properties advances. Laser technology harnesses coherent light for applications ranging from precision manufacturing to medical treatments. Fiber optic communications rely on light transmission through materials designed to minimize energy loss. Solar energy systems convert photon energy directly into electrical power, demonstrating practical applications of the mass-energy relationships we have explored. The absence of mass in shadows does not diminish their importance in scientific and practical contexts. Shadows provide essential information for navigation, timekeeping, and architectural design. They create microclimates that support diverse ecosystems and influence agricultural practices. Understanding shadow formation enables advances in optics, astronomy, and materials science, where controlling light distribution proves crucial for system performance. Future research in physics will undoubtedly uncover new aspects of light behavior and electromagnetic phenomena that further refine our understanding of these fundamental forces. Quantum optics, gravitational wave detection, and studies of dark matter and dark energy all involve sophisticated interactions between light, matter, and space-time that extend far beyond traditional optics. The principles established through our investigation of shadow mass provide foundations for understanding these advanced topics. The question of shadow mass serves as an excellent example of how scientific thinking approaches problems through systematic analysis rather than intuitive assumptions. While shadows might feel substantial due to their visual prominence and environmental effects, scientific investigation reveals their true nature as geometric absences rather than physical entities. This distinction between perception and reality underlies much of scientific progress throughout history. Our exploration concludes with a deeper appreciation for both the power of light and the significance of its absence. Shadows may lack mass, but they play essential roles in shaping the physical, biological, and technological systems that define our world. Understanding why shadows have no mass illuminates the fundamental principles that govern how energy, matter, and information interact throughout the universe. The journey from a simple question about shadow mass to a comprehensive examination of light's properties demonstrates the interconnected nature of physical laws and the rewards of approaching familiar phenomena with scientific curiosity and rigorous analysis.